Now let's go ahead and define the term statistical inference. It says that using information from a sample to infer something about a wider population is called statistical inference. And this is kind of the idea that we introduced in the previous video. However, let's look at, there's a couple issues, like the first bullet point. Because the results of a random sample include the element of chance, we can't guarantee that our inferences are always accurate. It was kind of like going back to the last example where we found that 4.5% of ninth graders carried a gun to school in the sample. But since that assuming that sample was purely random and did not include other forms of bias, which again, ideally, you can fill in the first bullet point on the next kind of part of the packet, as good samples are always chosen randomly. That was one of the key ideas from chapters 8 and 9, to remove as many forms of bias and error as we can. But because there's randomness in a random sample, there still is the element of chance, right? If we take a random collection of ninth graders, there's still a chance that that percentage of students is much higher. Like, let's say we got 6% of students carried a gun to school, or 2% of ninth graders carried a gun to school, right? That percentage that we get could vary wildly from sample to sample. That's the key idea behind a sampling distribution, is what are the different types of answers could we get, and what are the distributions of those different types of samples that we may collect. And so the second part is we can guarantee that our methods usually will give accurate answers, right? Like if like that 4.5%, usually, like typically, if again, assuming that it was from a purely random sample, that should be relatively close, and that's another key idea in an inference. So let's look at another example. Let's say the mean household income from a sample of 125,000 U.S. households was determined to be approximately $75,000. Let's just say there are 125 million households in the U.S. The question is, what would we conclude about mu? Remember, x bar stands for the samples average, and the goal is to take that number and try to say, well, what does this imply about the entirety? And what we conclude is it should be relatively close. But how close? That's kind of the issue at hand. Is like, is it going to be 80,000? Is it going to be 70,000? It's probably not going to be exactly on, but what are those sort of chances, and what are those sorts of distributions? And in chapter 15, we're going to be using the normal distribution back from chapter 3 to sort of imagine, okay, what is the likelihood that the actual mean of the population is close, and how close would it actually be at the end of the day? And we refer to this about statistical estimation. And, we could think about resampling this population of, let's say we did this again, and we did a different sample of 125,000 U.S. households, or re-randomized it. We could get an answer like 60,000 or 80,000 or 100,000. It just kind of depends on what homes are surveyed, right? Because there are certain homes in the U.S. that are extreme outliers that are valued at, say, $5 million or $10 million, right? If we got a couple hundred of those in our sample, the standard deviation would be much, much larger than if we only got a few of those, right? So there's certain data points which could be extreme, and that's the element of randomness, right? If we're random, we're likely to get some of them, but the fluctuation behind the numbers that we obtain will be different. And so obviously X bar will vary from sample to sample. Or if you took more houses or less houses, it could change those probabilities that we get extreme values within our sample. But one key idea is that if we keep taking a larger and a larger sample, our statistic X bar is guaranteed to get better and better and closer to the parameter mu. I mean, obviously, say you took a sample of 10 versus 100 households. A larger sample isn't guaranteed to be better than one inclination, but if you do larger and larger and larger, it will get better and better and better, right? Because you can kind of imagine, let's say you took 500,000 houses, or 1 million houses in the US, or 10 million, right? As the sample gets closer and closer to the actual data, we're bringing in more data points, and that average will eventually become correct, right? Because if we sampled literally the entire population of households, it will be the exact parameter. And it's sort of like saying the more and more we do, the better our data will become. And that's a key idea with sampling distributions. This is what's referred to as the law of large numbers. It says to draw observations at random from any population with a finite mean mu. As the number of observations, aka the sample size, increases, the average of those observed values tends to get closer to the mean mu of the population. Notice it says tends to get closer rather than being guaranteed. And that's kind of the point I was trying to make, is not every single observation will be better if you have more sample sizes, but the general trend is the more and more you take, you will get closer and closer to the mean eventually. And again, there's not really, you might be wondering, well, should I take 1% of the data or 0.1%? Like from the example, we had 125,000 households out of 125 million. That's 0.1%, which is not a very large percentage. But again, if you think about the logistics that would go into collecting data from 125,000 US households, that's a lot of data, very expensive, and it might not be practical to do anything more than that. The law of large numbers is foundational to a lot of fields such as probability and statistics as well. And a lot of businesses make their living off of this idea, like gambling on the stock market or betting, casinos, betting on sports, and so forth. So let's look at let's just try to think of a theoretical example of the law of large numbers. But let's say you bet $100 every year that the Padres will win the World Series, regardless of their chances and their odds of doing it. Now, jokingly, you'd expect your payout to be $0 because historically the Padres have been very, very bad, and usually if you bet on them to win the World Series, you're flushing your money down the toilet. Now, in this season and the last season, that's not been the case because they've actually had a relatively good team. And this year, they're actually one of the higher odd teams to actually win. But even if they were, notoriously bad, just imagine that you committed yourself to betting $100 every single year. The question is, what would be the payoff? Would you eventually win? And yeah, theoretically, you would eventually win. And the question is, well, how much money would you win? And if we're trying to determine if this is a safe bet or whatever, this would be called the expected value. And you would need to know the probability that the team would win every single year. But one of the points I'm trying to illustrate is there's eventually some final outcome, and it's kind of like the lifetime mean, which would be the entire population. Now, we don't know if the Padres will ever win, so this is all very theoretical, and it's hard to apply. But let's look at this chart to the right, which is calculating the mean of particular observations. And let's just say we're studying the age of college students at a community college or whatever, and just make up something that this chart represents to try to understand what's going on. But let's say we took one data point, and the first student we asked was 28 years old. And then, we took a sample size of, say, 4 or 5, and we got a much larger mean, say 34. And then we took 10 data points, 20 data points, 30 data points. And what we can see is that the average, as our sample size gets larger, is changing. And, it could be very, very drastic change at the beginning, because when you only take a couple data points, you might get more outliers. Or let's say we got a student who was 70 years old in our sample, right? That would grossly affect the mean. But over time, as we sample more and more and more students, the means that we're going to get for, say, doing 100 students or 1,000 students will get closer and closer to the actual mean of college students at a particular community college, or again, whatever it is we're studying. And so kind of looking at this, it's sort of like we're looking at X bar, which is the data that's being graphed in the red. And X bar changes as with our sample, right? The more we sample, we get different data. But mu represents the actual average of the entire population. And this is what the law of large numbers is saying, is that as we take a more larger and larger sample, it is guaranteed to get closer and closer to the mean over time. Again, there will be fluctuations because outliers or whatever, or biases within our survey methodology can affect these sorts of things. But the point, another conclusion we should make from this idea is that small samples are not as accurate as large samples, aka large samples are better at the end of the day. So let's do an example to illustrate this by rolling dice, and I'm going to move back to the packet here in a second. But In our example, what we're going to do is we're going to use probability of random probability to sort of try to illustrate this process of sampling. So what we're going to do is just, if you have a 6-sided dice in your house, like if you have Monopoly or whatever, have one handy, go ahead and grab it. Or you can also use Google to roll dice, which is what we'll do for the purposes of the online video. But basically what we're going to do is just going to keep track of our rolls, and we're going to examine the average value of our roll as we do more and more and more. So we'll start with 1 roll, and then 5, and then 20, and so forth. And then let's look at the mean that we obtain from our sample as we continue. So let me go ahead and end the slideshow. Whoops. And we'll track our answers on the packet. And again, let's go ahead and fill in the bullet points that I missed. But again, just to reiterate, good samples are chosen randomly. We can't guarantee that our inferences are always accurate when we take data from a sample, but we can guarantee that they usually give more accurate answers. And then as we take larger and larger samples, our X bar, which is our mean statistic that we're calculating from our data, is guaranteed to get closer and closer to the parameter mu, which we refer to as the law of large numbers. Basically, the more and more data we take, the better it will be at calculating what we're trying to find. And let's go back to our illustration. So what we're going to do is just roll a 6-sided dice and calculate the average. So if we did it once, and again, I have a 6-sided dice handy, but I'm just going to use Google and type roll dice, and it has a feature. And it goes ahead and it rolls a 6-sided dice. So let's just keep track of our rolls below. So we start with a 3. And so if we're looking at what's our average after 1 roll, I'll just call that X bar sub 1 to represent the mean after 1 roll. Our average is going to be 3. So, okay, cool. Doesn't mean anything yet because we just have 1 data point. Let's say we did it 5 times though. So let's roll it again. Click on it to roll another one. 6. I rolled a 4. I rolled a 3. And I rolled a 6. And just by, without having done any math, these rolls look a little higher than maybe you would find on average. And that's kind of the point we're trying to illustrate with a sampling distribution. So here, our total roll is 22, and our average would be 22 divided by 5. So our average roll actually went up quite a bit to 4.4. Again, on our packet, let's go ahead and keep track. You can do this your own or retry this experiment on your own to sort of see what sort of numbers you're getting. The point is there will be variation, right? Every sample looks a little bit different, but our rolls were 6, 4, 3, 6 after 3. So 6, 4, 3, 6. So those were our first 5 rolls. And what I'll do is I'll kind of just keep track of these rolls using making a little table here as we go. And so I'll also say, well, our X bar average after 5 rolls was 4.4. It got a lot higher. And the law of large numbers states that the larger the sample size, the closer it should get to the actual mean. However, in this case, these sample sizes are so small that I would still completely throw them out as estimators to the actual mean, because you need quite a bit more data. And the question is, how many data points do I need to get an accurate result? Well, the more you do, the more accurate it will be, and that it just depends on the circumstances. We'll kind of look at this later in the semester, say, well, what sort of sample size would we need here for a particular margin of error? But let's continue the little experiment. So let's say we were going to do it 10 times. So I need 5 more rolls. So let's do 5 more. 1, 2, 3, 4. Oops, I didn't mean to do that. I guess I'm just going to do it fresh. So crud. Let me just refresh this because I lost my other 5 rolls, but that's okay. So we'll just do 5 more. So 6, 1, 2, 3, and 1. And we'll go ahead and keep track of those as well for a total of 13. 6, 1, 2, 3, 1. And that would be a total of 13. So previously our total was 22. 22 plus 13 would be 35. And we now have 10 data points. Our average after doing 10 rolls is now 3.5. and we'd expect this to get closer and closer to the actual average. So we need 10 more rolls to get to 20, so let's just keep going. So I'll just refresh this, and let's just do 10 more in a row. So we got 3, 4, 3, 5, 6, and I'll just click it 10 times, and it looks like we have each of these totals. So let me go ahead and write those down. 3, 4, 3, 5, 6, 6, 3, 6, 6, 6. And if we were playing Yahtzee, we'd be very happy with a lot of these repeated rolls, but again, depending on the circumstance, these rolls, just by looking at them, it seems like these are high, right? It seems like we're getting higher than your average because we're rolling a lot of large numbers. We would not expect this to happen every single time we conducted this experiment. And this is the idea of sampling. If we're taking random samples from populations, sometimes we might get higher, the data points might be larger than we'd expect. Sometimes we might get smaller numbers than we'd expect. There is an element of randomness that affects with the sample size. And now doing 20 rolls, let's calculate our average. So we had 35 from the first 10. From the next 10, it's 48. That's a pretty huge difference in those different sample sizes. And so if we did 35 plus, 48, this would be our total from 20 rolls. And dividing that by 20, our average is back up to 4.15. And notice there's this fluctuation between the sample size. Now let's say we wanted to, we could do 10 more. We could do 100 more. We could do 1,000 more. This is something that you can also do in Excel. I guess let's go ahead and do that real quick just because it's pretty easy. If you want to generate random numbers between 1 and 6, there's an Excel feature called rand between. So if you do rand between, sorry, it's kind of small probably. Let me make this a little bit larger so you can see what I'm typing. But rand, let me redo this. So equals rand between will generate random numbers between 1 and 6. So if we went ahead and did this, basically we could simulate rolling a dice. And if we could drag our formula down to do it 10 times, and we could drag it over here, 4, 5, 6, 7, 8, 9, 10 to get, say, 100 dice rolls all at once. And if I wanted to take, what's the average, I could do, or the mean value of each of these dice rolls, I could then kind of select it by taking equal average of all of those. And what I would get is 3.44. But what I'm illustrating is the more and more we roll, we get this fluctuation in dice rolls. This would be a much faster way of conducting this sort of experiment given random chance. Let me go back to, sorry, I lost track of where I was, but we could then do 100 rolls and we could keep going, but notice we get a fluctuation in the mean value as we go. Okay, so now what's the actual mean? And so the question is, what's the mean of the actual population? Now, since this is a random chance of rolling dice, there is no such thing as not a population of all dice rolls that exist, but we could do this by saying that by taking the expected value of the experiment. And again, sorry, this is an idea that's not critical to our course, but just trying to express this idea of sampling distributions. And the idea of larger and larger data points should be getting closer and closer. But the actual average of dice rolls, that would just be the sum of each option, because each outcome is equally likely on a perfect unweighted dice, and dividing it by 6. So the proper mean, the true mean of rolling dice should be that, which is 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is a value of exactly 3.5. And actually what you might notice is that the average of taking 100 rolls was actually pretty darn close to the actual average of 3.5, assuming random chance. Because the more and more you take data, the more it will, the less likely you're going to have an extreme variance of outliers. Like if you remember from those 20 data points, we had a whole lot of 6s in those 20 rolls, which, since 6 is the highest outcome, would affect the mean, and it would give us a larger average than you would usually expect. If we got a lot of 1s, we would get a lower average. But excuse me, the more and more we continue the experiment, the less likely we're going to have that many 6s in our data, and it will trend more and more towards the exact actual mean, which is 3.5. And notice, when we did in Excel, we did 100 data points, it was very close to the actual average. This is an illustration of the law of large numbers. The more times the larger your sample, the better it should be at getting to the actual mean of the population. And we could extend this even further. Let's say we wanted to get 1,000 data points or whatever. We could just, I'm just going to drag this down arbitrarily, and, we have a whole heck of a lot of, actually, if I did just a few more, we would actually have 1,000. Now this is 100 by 10. Now we have 1,000 data points in our sample. If we wanted to know, well, what is the mean value, the mean roll of 1,000 dice, we would get 3.6. And notice again, it's not exactly 3.5, but it's pretty darn close. And if we re-randomize it, we could kind of calculate a new sample. Another thing about how the rand between formula works in Excel is if you hit enter and redo it, it will re-randomize it and do it again. So we can kind of see, well, what is a sampling distribution? Notice that we get about 3.5 re-randomizing each of these rolls. And if I did again, 3.57. If I did it again, 3.54. It notices a little bit higher than the true mean, but every single time it's pretty darn close to 3.5, which is, again, what I'm trying to illustrate here, the law of large numbers.